Okay, Ji, Bismillahirrahmanirrahim. So the next topic is thermal stresses and strains. As I was explaining earlier, that due to temperature changes, the different sorts of materials behave differently, and their behavior depends mostly upon their coefficient of thermal expansion. And as we already know, that materials do expand whenever they are heated, and they contract when they are cooled down. So, in general, different materials have their standard coefficients of expansion depending on their composition, their material property, their internal physical arrangement of atoms, and etc. So all of these things do matter, and to keep these things checked and undermined whenever we are designing the materials, we need to consider the weather conditions that these materials are going to be exposed to. For example, if we are talking about the different steel structures and the different facades that are used in the Dubai or the UAE or in the UAE, they are basically made of aluminum and steel, there are some tempered glasses that are used for the facade purpose. So what those things are designed are that they can sustain different temperature variations at night and in the day. So in the day, the temperatures might go up as much as 54 degrees Celsius, and then at night they might probably drop down to even 10 or 5 degrees centigrade. So all of these things do matter, and for that reason, thermal stresses and strains must be kept into account while designing materials. Now, uh, as we are discussing, there must be some specific conditions under which the material are undergoing. So we have to keep those in mind. The thermal effects might be some. They might arise due to temperature changes. There might be some misfits resulting from imperfection in the structure, in the construction, and pre-strains that are produced by initial deformation. So all of these external loads and external sources might produce some internal stresses in the material. Now, thermal stress is what? Thermal stress basically, if there is a material that could expand or contract, there are some basic information that we need to consider while solving for the thermal expansion. The first is the length, where L, which is the length, which is the original length of the body. Delta T is the rise in temperature. E is the modulus of elasticity, or Young's modulus. Alpha is basically the coefficient of linear expansion or thermal expansion, as I mentioned earlier. Then delta T is the extension of rod due to rise in temperature. So, keeping the simple strain equation or the thermal strain, it could be equated as change in length due to the rise in temperature divided by the original length. So this is simple equation for the strain. Now, considering all of this and the thermal expansion, the materials might also undergo some thermal stresses. So, for that reason, we are going to first define the thermal strains, which is also equal to, which is directly proportional to the change in temperature. So, thermal strain being directly proportional to the change in temperature, and when it is the directly proportional sign is replaced with the equation. So equation is equal to there is an alpha value that is introduced over here, which is known as the coefficient of thermal expansion. Now this alpha, as strain is unitless, so and the temperature unit is centigrade or Kelvin, so this alpha must have a unit that must be inverse to the centigrade or Kelvin. So that centigrade divided by centigrade would be cancelled out, and the strain would be as unitless as it normally is. Okay, so the unit for uh, alpha is what? Reciprocal of Kelvin, or reciprocal of degree centigrade. Now, stress is directly proportional to strain, and stress is equal to E into strain. Now we have already defined that the thermal strain is equal to alpha into delta T. So we replace that alpha into delta T over here. So sigma is equal to E into alpha into delta T. This is the general thermal equation, the thermal stress value that is used. And so now, right now we know both the values of thermal strain and thermal stress. So we are going to use these in the coming examples as well. The modulus of elasticity is generally, if we are talking about steel, it is 30 into 10 raised to power 6 psi, and alpha value for steel is 9.667 into 10 raised to power minus 6 inverse of degree centigrade. Okay, ji. So there is an example over here which quickly states that how important the thermal stresses are. A quick calculation from the preceding equation for alpha shows that a change in temperature of 100 degree Fahrenheit produces the same strain as a stress of 29,000 psi. So you can idealize that how important the change in temperature is. The internal temperature, if increased by 100 Fahrenheit degrees, the strains that could be introduced would be equivalent to that of 29,000 psi of stress, which is huge. Okay? This means that we need to keep the stresses under the allowable stresses condition. Thus, a relatively modest change in temperature produces strain of the same magnitude as the strains caused by ordinary loads, which shows that temperature effects can be important in engineering design. So it is very crucial that we do consider the thermal stresses, because uh, if the temperature variation is very low, it is not going to be that detrimental or that effective on the overall strength of material. But if we are talking about heavy and high temperature variations, only then the material is going to have a lot of stress or a lot of strain in it. And because of these things, the engineering design must have temperature effects being taken into account. Now, the using the same strain equation, strain thermal is equal to delta divided by L. We can also replace it using like we can equate it using the delta T is equal to strain T into L. Now, strain T, what is strain T? It is equal to alpha into delta T. So we replace it over here. So we are getting that the change in the length, or the as shown in the figure over here as well, there is a total length L, and because of a delta T or change in temperature, there is a change in length as well, which is known as epsilon T, or whatever you call it, which is the small delta T. Okay. Now these equations are going to be utilized for the calculation, as I mentioned earlier. Um, Please keep into account that whatever the stresses and strains that are being introduced with the help of external loadings, those are going to be there. Those are going to affect the material already. But the effect of thermal expansion or thermal contraction is going to be taken into account into in the same like in the same equation. For example, over here you can see that actual strain is equal to strain is equal to delta T minus delta divided by L. Now, what is delta T? Delta T is the thermal strain, and it is because of expansion. So with the whenever there is an expansion, we take it as plus, and there is an internal strain which is due to contraction as well, and that is because of the some applied load. Just over here, as mentioned over here, when rod is subjected to compressive load. So we are adding both of these over here, so that we get the overall strain in the rod. Similarly, we can have the overall stress in the rod as well using the same equation. We are going to use the same equation multiplied by E. So it is going to give us the actual stress in the rod, which is going to accommodate or accumulate the effects of thermal stresses as well as the applied loads stresses. Now, this is an example over here. 10-meter long steel rails are laid with a clearance of 3 millimeter at a temperature of 15 degrees centigrade. When the steel rails were placed, they were having a temperature of 15 degree, so they were given a clearance of 3 millimeter, and the length is how much? 10 meters. At what temperature will the rails just touch? How much, like there is going to be some expansion in the material, and there is some coefficient of expansion being provided over here as well, so it is going to expand obviously. But at what temperature both of these rails are going to touch each other? uh, what stress would be induced in the rails at that temperature if there were no initial clearance? If there is no clearance being given, the 3 millimeter clearance, then what stresses would be there? Assume alpha is equal to 11.7 micrometer per meter centigrade, and E is equal to 2200 gigapascal. Okay, so let's solve this. Now, the delta T equation, the delta T is equal to alpha into L into delta T. Now, delta T is already given to be 3 millimeters. It is going to expand by 3 millimeter only. We want to know what would be the final temperature of that. So 3 millimeters is given over here, is equal to alpha. Alpha is how much? 11.7 micrometer. Micro means 10 to the power minus 6. So we multiply it with minus 6, 10 to the power minus 6. Now, what is L? L is 10 meters, but the other units are 3 millimeters. So we, unify the units over here. So we multiply it with 1000. So 10,000 over here. Then TF, we don't know what is TF. The TI, the initial temperature is 15 degrees centigrade. We already know that. So solve it for TF. We find out to be the TF is equal to 40.64 degrees centigrade. At the temperature of 40.64 degrees, both of these rails are going to touch each other. Now, the next problem is, what would be this internal stress if there is no gap in between the rails? So for that reason, we would say that the the strain or the change in length is equal to change in length because of temperature. So now change in length is equal to PL over AE. Do you remember that? I hope so, because PL over AE is the deformation, that initial deformation within the material. Okay, now that P by A could be replaced with sigma, because stress is equal to force per unit area. So we replaced it over here for sigma. So sigma L divided by E is equal to, we are having the same equation, alpha L into delta T. Now it is simple. We just multiply the other side with E and cancel out the L on both the sides. So sigma is equal to alpha E TF minus TI. Now alpha is how much? This much. E is how much? This much. TF minus TI. So we are given to be having a stress of 60 megapascal when there is no gap in between. So you can idealize that how important it is to consider thermal stresses. Otherwise, thermal expansions. Otherwise, the materials are going to undergo a lot of stresses. The 60 megapascal is a huge stress. Now let's go to another problem. Calculate the increase in stress for each segment of the compound bar as shown in figure below if the temperature increases by 100 degree Fahrenheit. There is a compound bar, one is this one and the other portion is this one. This is aluminum bar, this is the steel bar. The cross-sectional area for this aluminum bar is 2 square inches. The modulus of elasticity is 10 is to 10 is to power 6 psi, and the coefficient of thermal expansion is this much. Similarly, the material or the descriptions are given for steel portion as well. The length of both the rods are also given, 10 inches and 15 inches. Let's read the remaining portion of the equation of the problem. Assume that the supports are unyielding and that the bar is suitably braced against buckling. So we are trying to, not come up with some alternative solution. We just want to know that what would be the stresses that would be, forcing both of these sides outwards because of the increase in temperature. We just don't want to consider whether these supports would yield or not. We also don't want to discuss whether if they are not yielding, so this rod might probably buckle. So we are not also considering that. We are just wanting to know that how much stress is going to be induced on both these sides. Now, towards the solution, the delta T. First, because this rod is expanding because of the increase in temperature, similarly this rod is also expanding, so both of these are trying to push each other away, you see. So delta T is equal to alpha into L into delta T. So what is delta alpha? 6.5 10 to the power minus 6 in case of steel, multiply by L. What is the length of L of sorry, a steel rod? It is 15. Multiply by 100 Fahrenheit. So this is the change in length or the deformation in case of steel. What is the deformation in case of aluminium? It is 0.0128 inches. This is also in inches. You can write it down. Now, when we are talking about the internal deformations, the deformations that are being produced because of the thermal expansion are going to be equal to the deformations in the material. Like the temperature deformations are basically deforming the material. What are they going to deform? They are going to deform the material itself. So that's why we say that the deformation in steel plus deformation in aluminium, the internal material deformations are equal to the deformations that are introduced because of the temperature. So PL over AE of steel plus PL over AE of aluminium is equal to delta T of steel plus delta T of aluminium. So this is simple. Now we also say that because both of these rods are parallel to each other, so the force P that is undergoing from one of it is going to be actually the force that is undergoing from aluminium. It is the force, also the force that is going through steel. Like it is going to be the same P. How would that be different? Yes, the stresses could be different because the cross sectional areas are different, but the force could not be different. Okay, because the system is in equilibrium. Okay, so P is equal to PST is equal to PAL. Now we solved for the given P. So P multiplied by L. What is L in case of steel? It is 15 divided by AE. A is how much? 1.5 square inches multiplied by E, 29 into 10 to the power 6. Similarly, we solve for P of aluminium, and then we add both of these. So we find out that the P, the force that is going through both of these rods is how much? 26,691.8 pounds. It is not going to be psi. Psi is a unit of stress. This is pounds. Okay. Now, stress is equal to force per unit area. So we solve for this. This P is going to be same for both of them, but the cross sectional areas are different. So we solve for the stress in steel and for the stress in aluminium. So then we are able to find out the psi's. And this is it. I hope it is clear. If it is not, you can re-listen to the audio and get to know that what we are talking about. And there are some self-assessment problems over here. I would wish you people to solve these, practice on these, and discuss on them if you want to in the WhatsApp group as well as in the LMS. Okay, thank you.